moment I will read the questions in the textbook. Yeah. Since the question asks to use this theorem to prove the convergence or divergence, then we should base on this theorem to prove it. Okay, not a definition. Okay, now let's see. So many, right? I will choose some to do it. For example, actually this is easiest. Okay, let's start from here. Example, and then 2.123. Okay, 3. A n equals 1 over n. Now, based on the theorem 2.4.2, I don't know if you still remember, okay? 2.4.4 says, if we have a monotone sequence, right? If it's increasing, then blah, 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 right? Then I explained, we can have similar results for decreasing sequence, right? Now, first thing is when you determine this sequence is decreasing or increasing. If it's neither decreasing nor increasing, that means we couldn't use theorem 2.4.2. Okay? Now, everybody can see that this sequence is what? Decreasing or increasing? Increasing. Decreasing, right? Everyone can see it. But anyway, you need to prove it. Why is this decreasing, right? Now, how to prove that it's increasing or decreasing? Use a similar equivalent result. Equivalence, right? In previous theorem 2.4.3, right? Let's see. This theorem, right? This theorem. Anyway, this theorem, right? This is of course for increasing. Now for decreasing similar. Okay. Now proof. Since an plus 1 over an equals 1 over n plus 1 over 1 n. Do we have this equivalent? Now, equivalent statements including a difference or a quotient, right? Wait, this time just use the quotient. If you difference, fine. Now this becomes n over n plus 1. That's 1. That's 1. Since this is true, so we know an is decreasing. Now, based on theorem, if it's greater than 1, it's increasing, right? Now, if it's less than 1, it's decreasing. We have the similar results, but we didn't. I didn't study in detail in the class, but you can imagine equivalent, similar results. This over this one, less than 1 means what? Means the latter item is smaller than the previous. The successive item is smaller than the previous item. That means decreasing. Right? Increasing means the successive one is greater than the previous one, right? So it's decreasing. Now, since it's decreasing, now in order to show that whether it's convergent, we need to see whether it's bounded below. Okay, if it's bounded below, then it's convergent. Okay. Now, with n using n's convergent, right? Obviously, n greater than 0 for all n. N is positive. So n is all n greater than 0 means what? Means 0 is a lower boundary. Lower boundary. Just means the boundary below. So an is bounded below by the a similar result to theorem 2.4.4. We know AN converges. Determine if the following sequence has a finite limit, so we should say has a finite limit. Has a finite limit. Okay. So in this question, you are not asked to find the limit. Everybody can see the limit is 0, right? But the question didn't ask you to do that. You are only asked to determine if the following sequence has a finite limit, this one, or this one, or this one, right? So this is of course in this question, the question didn't say to prove. Didn't say proof. So if you just give some explanation, it's fine. You don't need to give the strict proof. So based on the question, you can write your answer simply or more detailed. This is decreasing. Let me find an increasing one. Okay. Now since this is decreasing, now this is also decreasing, right? Now this is increasing. Now for example, for the first one, just show the first one. This is example 2.1. AN equals negative 1. Now once again, we need to determine it's increasing or decreasing, right? Now to find the anyway, we still use the quotient form. AN plus 1 over AN equals negative 1 over N plus 1 over negative 1 over N. This is N over N plus 1. So, wait a minute. Let's look at the theory. For an increasing sequence AN. What means increasing? Right here. This means only when AN greater than 0. Right? Here our AN is negative. So the result will be opposite. Okay. Now how can we use the theorem to explain? This time I can only use the definition because the theorem didn't say anything about a negative in sequence. Okay, so let's use the definition. Sorry for that. Now, based on definition, what means increasing or decreasing? Right? When you take the difference, to remember the definition for increasing or decreasing, we have definitions. This is increasing. Right? Increasing means AN less than AN. For all N less than n, then decreasing is opposite. Okay. Anyway, I want to show that this is increasing. We see that it's increasing. Okay. Now, based on definition, AN plus 1 minus AN. If this is greater than 0, that means it's increasing based on definition. Right? Now this is negative 1 over N plus 1. Minus negative 1 over N. Okay. Now this becomes 1 over N minus 1 over N plus 1. This equals N times N plus 1. Now based on definition, AN is strictly increasing. If you don't believe it, check the definition. What means strictly increasing? Anyway, no matter it's strictly increasing or just increasing or eventually increasing, as long as it's bounded for increasing sequence, if it's bounded above, then it's convergent. Now, why is it bounded above? Obviously, an less than 0 for all n can be. This sentence just means 0 is an upper bound, right? And since it's bound above, so by theorem 2.4.4, an as a sequence converges, has a finite limit. Now, so far, any question? So far, I have shown you 2 examples. One is decreasing and has a finite limit. The other one is increasing and also has a finite limit. At this time, let me show you an example that is infinite. Okay. Positive infinite or negative infinite. Okay. Or negative infinite. Sorry. For example, we can easily see that this one. This one, you see this one, I will just do positive infinity, right? Now let's just look at this one. Also use this theorem. 2.14. This is 1, 2, 3, 4, 5. Example 2, 5. A equals square root of n plus 1 plus, looks complicated. Okay. Can you see that, is this sequence increasing or decreasing? Can you see? It should be easy to see. Of course, increasing. What means increasing? Increasing means if n is bigger, then it's bigger. But if n is bigger, square root of n is bigger. Then whole thing is bigger. Right? That means increasing. What means increasing from a sequence? Right? Means if n becomes bigger, then the expression an will be bigger. That means increasing. If for bigger n, an becomes smaller, that means decreasing. Similar thing. So-called increasing or decreasing of sequence just like this. Okay. Now, anyway, let's show it's increasing. Okay. We'll just start from the definition to show that it's increasing. Okay. Use the difference. Okay. Note an plus 1 minus a. If this one is greater than 0, means decreasing or increasing. Right? If it's less than 0, means decreasing. Now let's see, it's positive or negative. This equals for an plus 1, it should be square root of n plus 2 plus n plus 1. This is for an plus 1, right? Minus the difference. So this becomes square root of n plus 2 minus square root of n. Obviously, this is positive. Right? But if you still couldn't see it's positive, I want to show you one more step. Okay? Remember, we learned even from college algebra, we learned rationalization. Right? This becomes now since it's positive, you shouldn't have any objection, right? Because it's a quotient form. Both the top and bottom are positive, so of course it's positive. Rationalization will become n plus 2 subject n. So, an is increasing, actually strictly increasing. But an is unbounded above. If for an increasing sequence based on theorem 2.4.4, it says if it's just two possibilities. If it's bounded above, then convergent. If it's unbounded above, diverge to plus infinity. Now you may want to argue with me, how can you know that this one is unbounded above? If I couldn't see it's unbounded above, let's see, is it bounded above? What means bounded above, right? Bounded above means an less than some n for all n. Right? This means bounded above, right? Now you can use proof by conjugation. We couldn't have such an n. Right? For any n you give an n, I just let n to be n squared plus 1. Squared plus 1. Then an will be greater than square root of n. Then this is square root of n squared plus 1. Then greater than n. So for any n, I can always find an. Given any n, I define n to be this one. Then this an greater than this n. So it cannot be bounded above. Right? This is proved by conjugation. So this means, so an has a plus positive plus infinite. For such kind of question, if it says use the theorem 2.4.4, the key point is first you need to say this sequence is increasing or decreasing. You even don't need to show why it's increasing, like what I did. If you can show it better, if you couldn't show it, doesn't matter. Just say this sequence obviously is increasing or decreasing, okay? And then second, you need to show that it's bounded above or not. Okay. Second sentence. Third sentence, based on the theorem, therefore, is convergent or not. Okay. Third sentence. Okay. Now let's see I'm not going to show everything. Okay. Let's see the homework. And this time I want to check the homework. Homework is 93 to 90. Let's see, okay. 4, 5, 6. Number 4, prove the sequence an with an as given. Monotone or eventually monotone. Therefore, you do need to use definition. Okay? Then it's B and E. B and E. Now, if you couldn't use the definition, or the definition not easy to do it, you can also use the theorem the equivalent. Where's the equivalent? You can use the equivalent statements. In your textbook is remark 2.43. Either definition or remark 2.4.3 to prove this question. Okay. Just like the equivalent statement I introduced in the slides. Okay, this is the first question. Second, number 5. Prove that for an eventually decreasing sequence an, there are two possibilities. an is bounded below, in which case Okay, when you see this question, you should immediately realize that you could use the similar technique as we did for which theorem? 2.4.4, right? Right? 2.4.4, it says for any increasing sequence, there are two possibilities. So your proof should simulate or imitate, right? This one. So when you do some homework, you can find a similar way from our class examples. So this is number 5. And number 6, determine whether the sequence given is convergent by determining on monotomic or boundary. So for number 6, your proof should be similar to what I did here, right? Yeah. If you want to write shortly, just 3 steps, 3 sentences, okay? Obviously, the sequence is increasing, for example. Obviously, it's bounded above by a number, what's your number, right? Therefore, by the theorem, this sequence has a finite limit, something like that, okay? So I hope this time my requirement to your homework is more clear. Okay, so we finish this section. Any question? Next is, now this time is once again we have to use epsilon and language. Cos, I don't know how to read it. When I was in China, we read Cauchy. I heard some mathematician in North America, they call it Cauchy. I don't know what pronunciation is right, because this is not American people, right? Cauchy may not be an American, may not be an English, maybe from, yeah, probably either French or German. So we don't know the exact pronunciation. Anyway, this is a mathematician's name, okay, sequence. First, we need to introduce the definition. Neighborhood. Here, the definition for neighborhood is actually, we should call this neighborhood as epsilon. Epsilon? Yeah, epsilon neighborhood. And GH. We call it epsilon neighborhood because this is actually an open interval, right? This interval means x0 minus epsilon to x0 plus epsilon. Can you see it? This set is actually this open interval. So this interval is centered at x0 with radius epsilon. What means radius? Means this epsilon. So we say an epsilon neighborhood is an open interval centered at x0 with radius epsilon. So the epsilon neighborhood. Based on different epsilon, we have different neighborhood. And the bigger the epsilon is, the bigger the open interval is. So so-called a neighborhood of some real number x0 means an interval, open interval, centered at x0 with some radius epsilon. This is neighborhood. From now on, I will use the for brevity. This means when I write MBHT, that means neighborhood. This word is too long. A deleted or punctured neighborhood of x0 means you can see the difference. The definition. What's the difference between a neighborhood and a deleted neighborhood? Deleted. That means some point was deleted, right? Which point is deleted? In this case, which point is deleted? X0. Yeah, x0, yes. Means that this is the neighborhood of x0. Now what means deleted neighborhood of x0? A whole, right? Open interval, but the center is not excluded. If you remember, in the definition of a limit in calculus 1, if you check the limit definition in calculus 1, what means limit x approaches x0, f of x? Okay. The definition, if this is equal to L, the definition is for any epsilon greater than 0, there exists delta greater than 0 such that fx minus L less than epsilon for any whenever x minus x0 less than delta and greater than 0. Therefore, in that definition, we have used the delta at neighborhood. Now, this is less than delta, so this is delta neighborhood, but deleted neighborhood. Deleted delta neighborhood. Definition. Accumulation point of a set Now the difference between real variables or real analysis and calculus class is, in calculus class, our discussion is always on some interval, right? But for real variables or real analysis, our discussion is usually on the set of real numbers. Such a set may not be an interval, may contain some isolated points. Okay. Therefore, in real variables or real analysis, the situation becomes more complicated. Okay. Now, for a set of real numbers that may not be an interval, for example, 1, half, 1, right? This is a set, right, of numbers. Actually, this means 1 over 1. This equal to the set 1 over 2 and from 0, 1, 2, right? Like this, right? So this is a set. This is a set of real numbers. This contains no interval, right? Of course, it's not an interval, and even doesn't contain any subinterval. Now let's see what's the accumulation point. That is your set of real numbers. A real number is 0.